Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to Module 5.5. Yes, this week we have talked about a number of concepts, and if you remember, we started with this idea of the second law. That is, we considered this general situation where you have a device, electrons come in with energy, and energy E1, thus N1 is the number of electrons coming in. They put E2, N2, and there is some amount of energy E0 from the surroundings. And the basic rules that we wrote down is N1 plus N2 is equal to 0, because after all, electrons, if they come in from one side, they must be getting out at the other. So total electrons coming in, that's 0. And the total energy is conserved, but the important thing that we have been talking about is this second law. And that says that when you look at this energy, the total energy that came into this channel, there are kind of two parts to it. You see, there is a part that's carried by the electrons, this mu1, n1, the part that came from your battery out here. And then there is the part that is heat that actually came in from the surroundings. And if everything were at the same temperature, then what the second law basically says is that this total amount of heat that you are taking in from the surroundings, that must be negative. That must be less than or equal to 0, which means that you cannot just take heat in from your surroundings and convert it into useful work. And if these different reservoirs are at different temperatures, then the general version is that this thing divided by T1, this divided by T2, and this divided by T0, that total, all three of these, when added up, should be less negative. So that's this second law, which we started with in Module 1. And then we talked about where that comes from, this idea of entropy. That is, we wrote this S is equal to K log W. Let me get a better pen here. Maybe this. S equals K log W, which tells you that, this is a measure of the number of states available to this reservoir, and which always increases with energy. So the more energy a reservoir has, the more the entropy, and it is this ds dE that is defined as the temperature of that reservoir. So these were the ideas that we talked about, and in the last module we talked about how this W, of course, refers to the total number of states of this entire system, but if the big system is composed of lots of little ones, then in terms of the probabilities of those little ones, you could write this entropy as minus K summation over I Pi log Pi. And one of the important, as an application of that, we considered this system of spins, a bunch of spins, which could either be up or down. And if all of them were up, then that would correspond to an entropy of 0. If all of them are like random, then it corresponds to an entropy of K log 2 per spin times n. So that's the random case. And this is the ordered case when they're all up. Now, what I want to talk about in this module is that, see, when a bunch of spins kind of go from this all up state to this random state, there's an increase in entropy, or what you could call a loss of information. And that also corresponds to a decrease in the free energy, because F is equal to E minus Ts. And in principle, first thing I'd like to explain is how, according to the basic second law of thermodynamics, the basic second law meaning this law here, we can show that in principle, when the surroundings change their free energy, so that the free energy actually goes down in the surroundings, you could, in principle, build a device to extract it, and that would be in keeping with the second law. So that's the first point I want to mention. And then we'll talk about actually a concrete device, as to, the concrete device that you could build to actually extract this energy. The energy that when a bunch of spins from all up goes into the random configuration. Okay. So first point is, how do you show that according to the second law, you could extract an amount of energy equal to the change in this free energy? Okay. So the first point to note is that these quantities here are actually denote the change in the entropy of that reservoir. So, and that's because, you see, earlier we had written, maybe I'll take this out from here for the moment. Earlier we had written this ds dE as 1 over T. What that means is the change in entropy of a reservoir at a given temperature is given by dE over T. So if you give a reservoir some energy, its entropy increases. So this E1 minus mu1 N1, if you remember, denotes the amount of energy just taken from the surroundings here. So that sort of corresponds to the decrease in entropy of this reservoir. Similarly, that one corresponds to the decrease in entropy of that, and this corresponds to the decrease in entropy of that. So what we are saying here is that overall, this is the decrease in entropy of these three things, and that must be negative. What that means is overall the entropy must have increased. See? Now, for this discussion in this module, I'll write this last one as minus delta S0. That is, as I said just now, that this quantity denotes the change in the entropy of that reservoir. And the reason I'm writing it this way is, when you consider a bunch of spins that are all, say, up, it is hard to define a temperature corresponding to that, because it's really not an equilibrium situation. If you had 100 spins in equilibrium, it would be 50 up and 50 down. So 100 up really is not described by any equilibrium distribution, and so it's hard to associate a temperature with it. On the other hand, we have talked about how you can generally define entropy in terms of this pi log pi. And of course, if they're all up, we know that the entropy is 0. And so, for this discussion, instead of E0 over T0, it's convenient to work with the entropy change. So I'll write that here, minus delta S0. And for this discussion, we'll assume that these two reservoirs are both at the same temperature. So just use T here. Okay. And let's take this mu1 N1 and mu2 N2 over to this side. So you'll have something like this. So the mu1 N1 I had here and the mu2 N2 I had here, I take them over, so I don't need them on this side anymore. Keep it here. Now, E1 plus E2, of course, must be equal to minus E0 because of this. So this whole thing I could write as just minus E0 over T. Now, E0, if you look at the way I defined it, it's this amount of energy going into that, out of this reservoir. So E0 is like the loss of energy from this reservoir. You see? So in that sense, minus E0 is actually like the change in the energy of that minus E0 itself. So I could write this overall then, instead of minus E0, I could write it as like delta E0. Because delta E0 meaning the change in the energy of this reservoir, which is minus E0, because of the way we have defined the E0. Okay. And now the point is that if you cancel out the T, what you get is take the T out from here, T out from there, and get a T there. And this is really like the change in the free energy of that reservoir. Okay. So what this is telling me, and noting that N1 is equal to minus N2, I could write this as mu1 minus mu2 times N1 must be greater than or equal to delta F0. So what is this quantity? It tells you, so let's say this is positive. What does that mean? It means that the way we have defined it, if mu1 is greater than mu2, it means like this terminal is like negative, that terminal is positive, and electrons are flowing in from the negative terminal, going out into the positive terminal. So that would correspond to mu1 minus mu2 being a positive quantity, N1 being a positive quantity. So it is kind of what you expect if you put a battery here. So a battery with its negative terminal on this side, that's what it would do. It would drive the system. So in that case, what you're doing is taking energy from the battery and driving your system. On the other hand, if say this thing went negative, what that means is mu1 minus mu2, it looks, this is negative, this is positive, but now the electrons actually flow this way. It flows into it. That corresponds to actually like charging up your battery. So if this thing were negative, then this rest of the system is kind of acting like a source of energy. So for example, if you had a solar cell, so this kind of corresponded to energy coming from the sun. Yes, you could use that to charge up your battery. You could take power from it. Or if this was again the case we are thinking of, a system of spins that is out of equilibrium, which are all up, then again what I'll show is you could design a device so you could use it to charge up your battery. Charge up your battery or light up a light bulb. In other words, do some useful work, whatever it is. And but that corresponds to this thing being negative. But what the second law tells you is that this must always be greater than the change in free energy. And ordinarily what would have happened is that this reservoir, the one that we have marked 0, that reservoir is, let's say if it is sitting at equilibrium, that means it is already at its minimum in free energy. So anything you do kind of wants to increase its free energy. And so the delta F is usually a positive quantity. And so in order to satisfy the second law, it's like this left-hand side has to be positive. But if we had a system that was out of equilibrium, so that its free energy was not quite its minimum, then you see in principle you could design a device. Then in principle, you see, as it relaxes to equilibrium, the delta F is a negative quantity, let's say minus some number, say minus 10. So then second law says this quantity must be greater than minus 10. Okay, but then it can be negative. It can be minus 8, for example. And that would still be in keeping with the second law. And what that means is you could extract energy from that system now. Okay. So if we are considering then a system of spins like this, so where you have a bunch of spins which are all sitting up, and since they're all pointing upwards, it means that the corresponding entropy is 0, as we discussed in the last module. And now if it goes to a situation when it is random, then as we agreed, the entropy is nk log 2. And we're assuming these are all non-interacting spins, so the energy hasn't changed at all. Whether the spin points up or down, energy is the same. Even whether they're all up or random doesn't matter. Energy is all the same. So there's no change in energy. So we could call that 0. So as far as the free energy is concerned, you could say, well, this free energy was 0, and here the free energy is E minus Ts. E is 0, so minus Ts, which is minus nkt log 2. So what the second law says then is that since the free energy has gone down by that much, in principle, you could build a device that would extract that much amount of energy out of this system. So, of course, you have to be clever. It doesn't tell you how you would build the device. That's up to you. It just says that, according to the basic principle, you should be able to build a device that would extract this energy out of it. And in general, of course, this is true of, change in free energy. And free energy, as you know, is this E minus Ts. And in a way, that's the kind of significance of that word free energy. It's like as if that's the energy that is available for taking out to do work. It's just that usually a lot of the free energy comes from a real change in energy. That is, something is in a metastable state with a higher energy than the ground state, and as it relaxes, in principle, you could extract that energy. What's striking about this example, the one we are considering, is there's actually no change in energy. Only thing that's changing is the entropy part of it. And so you might say, well, then you're saying I can extract this energy. I can use this to charge up a battery, or I could run a light bulb with it. But where did that energy come from? It didn't come from this system. The system didn't change any energy. It's just that because the entropy has increased, the second law says, in principle, you could just take some energy from your surroundings, from the heat in the surrounding, and convert it into useful work. It doesn't tell you how you do it. That's up to you. Okay, you see? So how would you do it? Well, that's the thing that is discussed in the notes. I'll try to quickly outline the idea. And that is, what you use conceptually in this case would be this anti-parallel spin valve. The one that we discussed, I think, a little bit in week 4 in this course. And we talked a little more about it in week 4 of the part 1 of this course. And anti-parallel meaning that this is a contact that is pointing, say, upwards. This is a magnet pointing upwards. And this one is a magnet pointing downwards. And for this discussion, let's assume we have a perfect spin valve. What that means is that from this magnet, you can have spins come in. All up spins come in that direction, but no down spins can come in or get out. Usually what happens is magnets have some non-zero efficiency. What I mean by that is non-perfect efficiency. That is, they inject up spins better than down spins, but it's not like they inject only up spins. But for this discussion, I'm assuming it's 100% effective. It only injects up spins, nothing to do with down spins. And the other contact then, one that's pointing downwards, that only injects the down spins. And these are the electrons in the channel that can go back and forth. And you have a system of fixed impurities in that channel, which could be like manganese impurities in a gallium arsenide channel. A semiconductor where there's electrons freely moving, and then there's these fixed things, which we have arranged to be all pointing up in the beginning. And every time one of these flips down, what happens is, this is this exchange interaction. That is, you have one electron in the channel that's, say, down, another electron in this fixed impurity which is up, and the exchange interaction causes them to flip. So, this one flips. And when this goes from up to down, one of these electrons goes from down to up. So you have an extra up in there and a vacant down in there. Okay. And because of the way we have constructed the device, what would happen is that this extra up would come out from this side. Why? Because we have these perfect contacts, and the only way an up can get out of the system is through that contact. And this empty spot that is left behind will get filled in from this side, because this contact again only can inject down spins. So every time you have one of these impurities flip, there will be one electron coming out this way, going out into the external circuit, coming back this way, and that is how you'd have a current flow outside in your, charging up your battery or lighting up your light bulb, whatever, what have you. So this would be the kind of device that one could build in principle, you see, to extract this energy that we talked about. That this, as the system changes from here to here, the change in the free energy at this nkt log 2, you could extract by building a device of this type. Namely, again, it's not meant to be a practical device to be built. It's more to illustrate the point. The second law says you can do it. This is a discussion of how in principle you could actually build such a device using this anti-parallel spin valves. So we'll finish this up in the next module.